Electromagnetic waves. In this video, we'll talk about Maxwell's equations and describe how they predict electromagnetic waves. We'll derive the wave equation and then solve it and look at that solution. The discussion about how waves behave, all the different parameters that describe the waves, that will come in following videos. Maxwell's equations predict waves. So let's look at Maxwell's equations, and we'll call this in source-free media. That means we're not going to have any currents or any charges. So just imagine this being in outer space somewhere. In this case, we have the curl equations, we have the divergence equations, and then, of course, while not strictly Maxwell's equations, they always go along with Maxwell's equations, it's the constitutive relations. And it's this set of 6 equations that fully describe electromagnetic fields. It will turn out for waves, it's primarily the curl equations that we're concerned about. And what we'll do is we'll take the constitutive relations, substitute those into the curl equations to eliminate the D and B fields, and we'll look at this just in terms of E and H. We're not missing any information by doing that. We'd have all the same conclusions had we done it with B and D, but E and H seems to be the most typical way to do this. So we'll start with the curl equations. And let's look at the one on the left. What this essentially says, if we have an oscillating magnetic field, it will have an oscillating electric field circulating around it. This del cross E is the curl of E. That is the tendency of the electric field to be rotating around some axis. So if that is non-zero, that places the magnetic field through that axis of rotation. This works both ways. We could start with a circulating electric field that would induce a magnetic field around through the center of that, or we could start with a magnetic field and we'd get an electric field around that. Now, the other curl equation just really swaps the roles of E and H, but essentially says the same thing. If we have a circulating magnetic field, we will have an electric field through the axis of that circulation. Or if we start with the electric field oscillating, we will induce a magnetic field circulating around it. Now notice the J omega. This means we're in the frequency domain, so we're not talking about static fields. We're talking about fields that are oscillating. So here we are. We have an equation where if we have an oscillating H, that will produce an oscillating E circulating around it. But then the other equation says that oscillating E will then induce magnetic fields oscillating around it, which then induce electric fields, which induce magnetic fields, which induce electric fields. And it's the coupling of energy or the exchange of energy between the electric and magnetic fields that actually leads to waves. So it's Maxwell's curl equations that predict waves. So what's one way to envision this? So let's start with an electric field, and it is oscillating. Well, we know from Ampere's law that that's going to induce a magnetic field circulating around it. Then we can focus on a magnetic field slightly to its side, and just one of those. We know there's a whole bunch, and each one will then produce more electric fields, but let's just focus on this one. We have an oscillating magnetic field, and notice it's oscillating perpendicular to the original electric field. Well, this will then induce an electric field circulating around it. And like we did before, we can look at one of the electric fields just right next to it, and we're kind of back to where we started. We have an oscillating electric field, which will then induce yet another oscillating magnetic field, and this just keeps repeating. And so I kind of envision in my head this little looking like chains of fields. But this is just showing propagation along a single axis. Every single one of those new induced fields induces other fields, and it's a pretty complicated process. And if we start with just a single oscillating field, in fact, we'll get sort of this donut-shaped radiation pattern from it. Derivation of the wave equation. It was Maxwell's curl equations that predict waves, so it makes sense then that the wave equation comes from some kind of combination of the curl equations. And in fact, that's exactly what happens. We substitute one into the other, and we get the wave equation. So notice I'm not starting here with the pure curl equations. These are the curl equations with the constitutive relation substituted in them. And these square brackets here means that these could be tensors for anisotropic materials at this point. We're not going to go too deeply into anisotropy, but I'm just retaining it here for illustration purposes. The first thing I'll do is I'll take this first equation and solve it for the magnetic field. That's pretty easy to do. I just take this group of constants here and bring it to the other side. So now we have an equation expressing the magnetic field. Well, I can take this equation for H and plug that into the second equation. And in fact, that's exactly what happens here. So here is that second equation, del cross, and this was the magnetic field, but we substituted in what we found from this first solution where we solved the first equation for H. Now at this point, and this will bring it what we have on the other slide, we have this minus j omega. That is a constant. That's not a function of position at all. So that can come to the outside of this curl operation, and we can bring it to the right-hand side of the equation. So this is as far as we can take the wave equation. And it's not a very useful form. We won't use this to do any kind of analysis. That would be incredibly difficult. But it is used a lot in computations, in numerical computations. If we're solving waveguides or simulating fields propagating through devices and stuff like that, we actually use this form of the wave equation. Well, why can't we take this further? That's because this is the most general case. This permeability here might be a function of position, in which case we can't just take it to the outside of the curl operation, which would let us simplify this, because the curl operation is spatial derivatives, and if this is a function of position, that's not a zero thing, and we can't bring that to the outside. So for the general case, this is our wave equation. Now let's talk about the special case where our wave is in some kind of infinite medium that is linear, homogeneous, and isotropic, or commonly called LHI media. Well, first, if it's isotropic, the permeability and permittivity are not tensors, and they reduce to scalar quantities, which is what we'll do throughout this course, but I will briefly mention anisotropy, more just to suggest that there really is a deeper set of theory and principles here that's very interesting, but also a lot more complicated. So our mu and epsilon are now scalar quantities. Second, because this is homogeneous, that means the material properties are not changing. They're constants. So we can take this permeability then, since it's a constant, to the outside of the curl operation and then bring it over to the right-hand side of the equation. And you can see we already have a simpler looking equation, but in fact, there's even more we can do with this. This double curl we can simplify further. So let's look at this double curl. Well, we know from the beginning of the course, there is this general vector identity that says the double curl of any kind of vector is the gradient of the divergence minus the Laplacian of that vector. And I wouldn't worry too much about trying to get physical meaning out of that. We discussed this earlier in the semester. Just think of this as a general vector identity that we can apply to the left-hand side of our current wave equation. So let's just go ahead and immediately apply that identity. Then what I'll do is I'll just rearrange terms. And on the left side, I'll retain this Laplacian of the electric field plus the omega squared mu epsilon times the electric field. And I'm going to bring this other term to the right-hand side. This is the gradient of the divergence of E. And what can we do with this? Well, this divergence of E looks a bit like the divergence equation, and we would like to just set that to 0. Well, the problem is the divergence equation says del dot D equals 0, not del dot E. So let's take a look at that divergence equation, and let's put it in terms of the electric field E to see if we can do anything. So del dot D equals 0. Well, we know through the constitutive relation that D equals epsilon E. At this point, we know that epsilon is a constant, right? Because we're making this LHI, linear homogeneous isotropic approximation. So epsilon's a constant, can come to the outside of this, and then we can divide both sides by epsilon, and 0 divided by epsilon is just 0. So here we've shown for LHI media that del dot E is also 0, not just del dot D. Well, that's great. We can apply that to the right-hand side of the equation above, and that del dot E is 0. So we arrive at the final form of our wave equation for LHI media. It's important to understand that this is for LHI media. Even though if you go to Google and you Google the wave equation, this is very most likely what you'll pull up. Well, it's for the special case of LHI media. But when we analyze things on paper, this is the form that we almost always use. Let's simplify this a little bit more. Remember this omega squared mu epsilon sitting in the wave equation? Let's just call that k squared. We're not talking too much about the physical meaning of these parameters, but this k will be called wave number, and that's something we'll discuss extensively later. So we can just let k squared be this omega squared mu epsilon. Similarly, we have something called the complex propagation constant. And again, I'm not going to put too much meaning into that yet. That will come later. And so these two things are related. Gamma is jk. So in my mind, these are practically the same parameter. You know, their real and imaginary parts have kind of opposite meanings to each other because we have this j constant sitting here. But it's two ways that we can just simplify the wave equation. So this lets us write the wave equation one of two ways. We can write it just in terms of this k squared, and we can solve it in terms of k squared, or in terms of the gamma squared. And just due to how they're defined, well, one has a negative sign, the other does not. We have two different versions of the wave equation, one having a negative sign and the other not. Really not a big deal, just two different ways to simplify the wave equation. Solution to the wave equation. So we have the wave equation, and we can expand this in Cartesian coordinates. We can expand it in any coordinate system. I think it makes the most intuitive sense right now to do this in terms of Cartesian coordinates. This is a vector equation right now. So we can expand that. So we have essentially the Laplacian of the electric field E plus k squared times the electric field E. Well, the electric field E has an x component, a y component, and a z component, and we'll put that in for both occurrences of E. At this point, we can multiply everything out, right? So we're applying this del squared with each of these components, and then multiplying the k squared on each of the components. So we've just spread everything out. Next, we can notice here is an x component of whatever's on the left, and there's another one over here. And there's a y component and another one, and a z component and another one. So we can group everything that goes with the x component, everything that goes with the y component, and everything that goes with the z component, and we end up here. Now notice what is multiplying each of these components looks like the wave equation. And in fact, it is the wave equation, but each one of those is a scalar wave equation. Since these are separate components, each one of those has to be independently satisfied, and they become independent equations. So in fact, for LHI media, we're going from this single vector wave equation to three independent sets of scalar wave equations. Now, they all look the same, so they're all going to have the same general solution. Now, from there, the general solution, whatever constants fall out of that, may change due to boundary conditions and all that, but they're going to have the same general solution. So let's just write the wave equation this way, not even bother writing the subscript, whether this is x, y, or z, because we can solve that and then apply that same general solution to all other field components. I wrote again this wave equation that we're going to solve. Let's remember this is actually one of the field components, But since each of those field components has the same wave equation associated with it, I'm not even bothering to write that. So at this point, I could hand that equation off to a mathematician, not even tell the mathematician what it is or what it means. I'm sure if they're smart enough, they'll say, oh, that looks like a wave equation, but they could solve it for us. And they would give us an answer like this. So the solution to the wave equation is complex exponentials. And so in front of the complex exponential is a complex amplitude, so it could affect the magnitude and phase of the wave. And then we have the complex exponential itself, which is describing the oscillation of the wave. The positive superscript is indicating that this is corresponding to the forward wave. And since we're using the negative sign convention, we have a negative sign inside of our complex exponential. But this is describing a wave moving in the positive k direction. K is something later we'll call the wave vector, and I'm not getting too much into the meaning of these parameters. That's something we'll discuss later, but suffice to say it's the direction of the wave. Now, similarly, the other term is the backward propagating wave. And so the negative superscript indicates this is the complex amplitude of the backward wave. Since we're using the negative sign convention, a positive inside of our complex exponential means there's a wave traveling in the negative k direction. So we could apply that general solution to the x, y, and z components, and we would have a set of 6 scalar solutions. Well, remember, those were all components of a single vector wave equation. So we can tie all of these back together again and get a vector solution to the original vector wave equation. And it looks very similar. We have the same complex exponentials going on here. It's just that what was the complex amplitude and a scalar quantity is now a vector quantity, but it is still the complex amplitude. It is describing the amplitude and phase, in this case of the forward wave, for the x, y, and z components all at the same time. And then this, what was the scalar complex amplitude for the backward wave, is now the vector complex amplitude of the backward wave because it's talking about the amplitude and phase of the x, y, and z components. So rather than keep writing forward, backward wave, we want to start the discussion about just a wave itself and talking about polarization and amplitude and phase and all these other things and meanings of parameters that will come in following videos. So let's just look at how we would express a single plane wave. And we can do this in the frequency domain or the time domain. In this class, the frequency domain will be the most common. So we would write it this way. And instead of having an E naught indicating this vector complex amplitude, we're going to write this as a vector P because it'll turn out that this term will describe the polarization of the wave. That's the direction and the behavior of the electric field as the wave propagates. And so this polarization vector is describing polarization and amplitude and phase. And then, of course, it has this complex exponential. We're using the negative sign convention, so we're talking about a wave traveling in the positive k direction. Now, in the time domain, we'd write this slightly differently. We have the polarization vector out in the front. Now, if this has a phase associated with it, we have all real numbers now. We can't really do that. We would have to take the phase of that and put that explicitly in the cosine. So I'm kind of skipping that right here. Also in the frequency domain, we had an implicit omega t. We're not really writing the time oscillation. We just kind of remember it's there when we're writing phasors. But in the time domain, we actually write the omega t, and then we have the minus k dot r. So the r is the vector position. That's the x, y, z. E is the total electric field. That's the thing that actually matters. Everything else is just a piece of the pie. This electric field is the total pie. And as I mentioned, P is the polarization vector. K is the wave vector. That's going to have a lot more meaning for us in following videos. Omega, we always just call the frequency, but it's actually the angular frequency. It's in units of radians per second. This is not the variable that is ordinary frequency that we would write as hertz or megahertz or gigahertz. That would be F. That's the ordinary frequency, and they're related just through 2 pi. So instead of being cycles per second, F, omega will be radians per second. And then, of course, T is time. Let's talk about the magnetic field component, right? We just went through all this work to write the electric field component. We could repeat everything we just did and get the magnetic field component. We would have the exact same equation as the electric field, but then we would just have 2 independent set of equations, and it's not really telling us how they're related. So I like to do this differently for the magnetic field. I'll solve the differential equation for the electric field, but then I will take that expression, substitute that into one of Maxwell's equations, and get the equivalent expression for the magnetic field, but then the relation between the two is apparent. So there is an electromagnetic wave in terms of the electric field. We will use Faraday's law and substitute this expression for the electric field into that equation and then solve it for H. So we just plug in what we had for the electric field, and when we solve for H, this is the expression that we get. And this is meaningful. We have the 1 over omega mu, and okay, so the amplitude is scaled in some strange way, but we have a cross product here between the wave vector, the direction of the wave, and the polarization vector, which is the direction of the electric field. Remember one of the properties of a cross product. The answer we get is another vector, and that's good because magnetic field needs to be a vector, but that vector is perpendicular to both K and P. So the magnetic field is perpendicular to the direction of the wave and also the electric field. So K, H, and E are all perpendicular to each other. And that's the origin of what we will call transverse electromagnetic waves, and it just has to do with the properties of cross products. Let's repeat this, but much more briefly, but in terms of this complex propagation constant gamma instead of K. Well, we would have had this single scalar equation in terms of gamma. Remember, this could be the X, Y, or Z component. We didn't bother writing that since it's the same equation for all of them. And our mathematician could solve that for us, and we would write a forward and backward wave. The general expression would be written very similarly, but notice there's no J here, and that just has to do with how the gamma and K are defined, but the gamma becomes a vector just like K became a vector. And then we could solve for the magnetic field component by plugging this into Faraday's law and getting this new expression. And notice the magnetic field H is perpendicular to gamma, which is also the direction of the wave, and the polarization vector. So it's still predicting transverse electromagnetic waves. And just remind us how this gamma and K are related just through this constant J. In my mind, I'm really thinking J and K are the same thing, but they're not. We interpret the real and imaginary parts differently because of this J, but it's serving the same purpose. So it blurs in my twisted mind, I guess. So let's visualize electromagnetic waves. And this is a whole direction I could go down of, what do waves physically look like? And it turns out it's not that practical to actually draw the waves in terms of what they physically look like. So we have these other things we do that at least try to convey their properties. For example, a plane wave is a volumetric thing. It is of infinite extent. Well, nothing in this diagram looks like it's of infinite extent. Well, how do you even draw something that's of infinite extent? So what's actually being shown here are the electromagnetic fields just along this z-axis. And we can see that I'm pointing, in this case, the electric fields along the x direction, although that could be pointing in any direction. But without loss of generality, we can say the electric fields are in the x direction. That would definitely place the magnetic fields in the y direction because they're required to be perpendicular to both the electric field and the direction of the wave. Notice I'm also drawing the magnetic field smaller than the electric field. That kind of goes back to that constant, that 1 over omega mu. And later on, we're going to write this more intuitively in terms of something that's called the impedance. But in general, the magnetic field is much smaller than the electric field. In fact, it's 3 orders of magnitude smaller. And I'm not drawing near that here. If I were to draw this to scale, you wouldn't even see the magnetic field. So I had to lie a little bit in this or exaggerate the amplitude of the H just so that we would see it. But it is perpendicular to E, and we're just drawing something confined to the z-axis. So in our minds, we sort of have to imagine this happening everywhere. What on earth would that look like? Well, here's one way to visualize that. This is crazy busy and is why people don't visualize it this way. But this is much closer to what the wave would physically look like. It has direction and amplitude and phase, and it's all varying everywhere. And if you look at this close enough, you can see the wave phenomenon, but it's so busy, it's not really that useful of a figure. So what we saw on the previous slide is going to be much more typical about how we draw waves, but it really does deviate from what they might actually physically look like. From the bottom of my heart, thank you so much for using EMPossible. I want to create more videos, and I want to continue to improve how electromagnetics and computation is taught online. To do that, it will really help me if you can like this video and subscribe to our channel. I also want you to know we have a lot more content that you may not be aware of. See everything we have to offer at EMPossible.net.